Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about a currently hot topic, SpaceX Raptors 3. So let's dive deep into it. So before we dive deep into Raptor itself, we have to understand why the Raptor, like why the heck we need Raptor. Because here's the deal, SpaceX built Merlin and this puppy was very successful. How successful? Basically, it made SpaceX daddy and flat out ended many small rocket competitions and old competitors also. Like how serious this was? Well, there is a very good rumor and there is a very good chance that by the end of 2023, ULA would be sold to someone else, most likely Blue Origin. So that should give you a context like how big disruption basically Merlin engine cost, because everything around SpaceX runs on this puppy Merlin, and Merlin has done amazing job flat out. Like there is no competition. There is 200 planets and almost that many companies, basically government and private, but SpaceX can single-handedly bitch slap all of them. It's not even funny anymore. It's like, dude, seriously, others have not caught up yet. So they have been like, oh, we have been reusing rocket for 6 years. Everybody else is like, we're gonna try soon. It's like, you get the point. Like it's genuinely successful engine. So what the hell is the problem? If it's that awesome and it worked, we have real world data, then what's the problem? It was like basically this was Mark 1 tool, and because of this tool now they're dreaming much bigger. Now their dreams have much bigger wings, and at this point in time Merlin is like, bro, I got this. Like this is my maximum oomph that I can give you. That's it. I cannot become any more refined, more improvement. Because here's the deal, fuel and oxidant, if you know the chemistry, you know how maximum energy you can get out of it. Like there's a limit to that. It's not like, oh, we can keep improving, you can improve in other vectors, reusability, longevity, those things, awesome. But in terms of raw grunt, it's kind of reached a maximum point. So they need something serious. Why? Because Mars needs a lot more love. Basically, this is good, but Mars is like, nah, bro, I'm not getting wet with this. Like you need a lot more oomph to, carry enough water to Mars to make it wet. So Mars needs a lot more love, like flat out. So Starship is the vessel that they are designing, and primary requirement of getting more oomph, because again, oxygen is fixed. Whatever fuel you are using is fixed. How much amount of joules it has, it's fixed. So how do you improve it? Well, you improve the efficiency factor, meaning if this is, let's say, 80% efficient, you make something that is 95% efficient. You cannot touch 100%, but you get the point. Like that's another vector. If fuel and oxidant flow is limited, that's the another vector. You make it more efficient, and making it more efficient even by a little bit yields very big result. And because SpaceX is dreaming so large at this point in time, they need something more powerful, hence Raptor. So what was that dream demand list? Like, of course, you have a dream, you will create a demand list. This is what needs to be done. So the demand list is basically more thrust. I have specified Raptor can be modified like to endless number of times, endless iterations, which they have done, like Mark 1, Mark 2, Mark 3, Mark 4, Mark 5. They have done a lot of it. But here's the thrust is not going much better. Like they grew a lot in thrust from Mark 1, and right now they are on block 5. They improved a lot in early days, but now they are not improving. And they cannot, like if you keep pushing it, it's not going to improve that much. It will be like, yeah, now we can carry 500 kilograms more on 20-ton rocket. So it's not going to be that big of a deal. So they need more thrust from day one, more thrust. And this also has another benefit. Can you make a giant Starship with tiny rocket engines? Yes. You'll just need way too many engines, and that's inherently bad, because there is a rule number 1 in engineering. Complexity is the enemy of reliability. Meaning, the higher the number of engines you have, the higher the manifold, higher the stuff that you have to deal with, more likely it's to go boom rather than actually going to orbit. So they need something that will reduce the unit count. Basically, oh, we want to transfer 100 ton to low Earth orbit rather than having 50 engines. What if we can do that in, let's say, 35 engines? That's the whole point. Reduce the number of units needed. And in principle, because again, they are focusing on Mars, in principle, propellant mix, whatever they are using, should be manufacturable in Mars. Basically, it should be Mars manufacturable, not mass manufacturable, Mars manufacturable, in situ utilization, at least in principle. Can it really be done? In principle, yes. Rocket, no. Why not? Again, remove the scale needed. The issue is that rocket also needs a bit more extra love from other things, which includes helium and nitrogen. Those things are not easily available on Mars. So again, right now Mark 1, but again, if you do not have a good Mark 1, there's no point of developing further. So they are, in principle, designing the foundation that in next 20-30 years can be used in such a way that it can truly go to Mars. If the foundation is like not suitable, it's not going to go anywhere. So this was the dream list. then it has to be much higher in terms of reusability, because SpaceX realized one thing very early on, is that everybody talks about rocket as a prestige project, and it was prestige project back in the, like, in Cold War. It was a prestige project. People were like, blank check, go boom. And people did, like, amazing engines were built, amazing rockets were built, there was no discussion about that. But here's the deal, now it's a different era. This era is money sensitive, so you have to make it cost effective. How do you make it cost effective? You make it reusable. Basically, everybody makes a rocket, launches it and eats it. You are like, hey, what if I don't eat it, what if I catch it? So that's the core aspect. And Merlin has proven, like, even with a sooty engine, why the heck this puppy goes white and comes black? Because it's sooty, because the fuel is kerosene. Now, problem with kerosene is that if you burn it, in principle, it should only give you water vapor and basically carbon dioxide. In reality, it generally gives you options. Basically, there are carbon bonds that create what you call soot, and that soot is sticky. How sticky? That even in a rocket exhaust kind of environment, especially in pre-burner area, it can clog up system. In pre-burner, it's like a miniature rocket, and it's like, no, I'm gonna clog up in a miniature rocket. And that's why it sticks so thoroughly. Like, it's very, very cloggy because of the long hydrocarbon chain. There's a very good chance a hydrocarbon chain may react differently, rather than just breaking and becoming like, water vapor and carbon dioxide. It's just like, nope. So there is a whole chemistry about that. But again, inherently the fuel is dirty. So even if you are burning 85% of it or 95% of it efficiently, that 5% will make your white rocket into black rocket. So fundamentally not good. And not to mention, it clogs up things eventually. So no matter what you do, after a while the rocket system will be like, bro, I cannot be refined anymore. Like, I cannot be refurbished anymore. It will be just too far gone. In principle, everything will look intact, but it's just like, you open it up, everything will have a layer of soot. That is like, cleaning it will cost so much that's like, bro, build a new one. That's why this puppy are limited to, like, reuse of 10. Like, 10 is optimum. You can push it beyond that, but like 10 is like GG. Don't even think about it. After that, it's like, do we really need to? Okay, we are not focusing on like resources on making new Merlins. We are focusing on Raptors. Okay, then we can, stretch it a bit, but it's not something that you are easy or smooth. Again, the only engine that even comes close to this, in principle, is RS-25 engines for built for space shuttle. And the reason for that was space shuttle was running on the cleanest fuel known to man, that is hydrogen. Meaning, even if you do nothing with it, it's gonna burn. So the best output is gonna be water vapor. The worst output is water vapor. You don't have to think about it. It's very good, which they called steam cleaning the rocket engine. So everything was awesome about that. Consequence, that puppy has weak. Hydrogen is weak. It does not have power. Like, to give you a context, compare the fuel tank size of space shuttle, which had a freaking solid booster to aid it. Compare that to stage 1 of Saturn V, which had kerosene. So kerosene has like some big horsepower, like serious horsepower, and that's why like Falcon 19 is so successful. Kerosene does have power. It is sooty, but it is powerful. So they need something in between. Basically, hydrogen is super awesome. If they make an engine out of hydrogen, there is a good chance they can easily get 100 reuse out of it, but it's too weak. Kerosene, too powerful, but too dirty. So they need something in between. So these are their demand list. So what is in between? Methane, CH4. It gives you the cleanliness of hydrogen and oomph of RP1. It's basically in between. Do not expect like, oh, it gives you same specific impulse as hydrogen or say, thrust as basically kerosene. But it's very close to like, efficiency and cleanliness of hydrogen. It's more closer to hydrogen rather than being closer to kerosene in terms of thrust. So we look into the design aspect of it. Well, this is a complex process. This is how complex I can go, and trust me, the level of complexity I'm gonna go in, that is baby level for actual rocket engineers. So this is just a rough idea if you want to understand, okay, what exactly is going on. So let's understand the key points, then I'm gonna try my best to describe this graph. So first is full flow stage combustion cycle. What does that mean? That simply means this is efficient. Why it's efficient? In the last engine, you must have noticed there is a pre-burner, and it's just letting gases go, the ugly gases, the sooty output. So why is that? Again, it's the easiest, cost effective. Consequence, you're just wasting fuel. That is unburnt fuel. Inherently, you have not extracted energy out of it. That's wasteful. And you're doing it to every gallon of fluid you have. It's unwise. So full flow stage combustion cycle has no exhaust other than the rocket exhaust, meaning every amount of joules you have, megajoules you have, you're going to get out of it. And it's going to go in one place where you want it to go, that is rocket exhaust. No leakage. It's not going to piss itself as like, it's like rocket is going and it's not going to do that. So closed cycle, that's awesome. Full flow, meaning that like these things are awesome. Now, it has electrical torch igniter. Now, there is two reasons why that is there. First reason is that Falcon 9 had a basically Achilles heel, that is TTAB. Now, again, they are designing things to run in principle on Mars, and not to mention TTAB has run out in previous mission where Falcon 9 could not be reused or landed properly simply because they could not reignite the engine because TTAB. Now, why did they needed TTAB? Because liquid oxygen combined with very cold kerosene generally does not burn, and kerosene is very hard to ignite on its own. That's in room temperature. If you have pre-cooled kerosene and you have cryogenic oxygen, yeah, very difficult. So they needed some love-making chemicals. That love-making chemical is TTAB. Now TTAB is one of those things that's like if it touches oxygen, it goes boom. Like it is so reliable in going boom that we used to use this puppy in SR-71 because SR-71 had a tendency to catch on fire. If they used normal JP1 into it, they built a special formulation, JP8 I think, or whatever formula, you can write it down. They used a special jet fuel mix for it. Now consequence, it did not burn easily. Consequence, electrical igniters were unable to ignite it. So what did they do? TTAB. And that was the limiting factor of SR-71. It's like how long a mission they can do. It was not the fuel part nor the engine heating part. They could shut down the engine to cool it, and again it had 2 engines, so it had enough redundancy. Things can be done. Is the problem was, yeah, they're gonna run out of TTAB, so they can turn off the engine without any issue. They can't turn it on if they run out of TTAB. Same basically SpaceX learned, like TTAB was a good solution but not a long-term solution, and again it also creates another plumbing hazard. And imagine doing TTAB flow to so many engines. So they are jumping to electrical torch igniter. Now, why can they do it now? Well, things are clean. For example, methane, gaseous oxygen, even at very cold temperature, is very easy to ignite. At that point, they are ready to make love. Like they're ready to. They're just ready. So little bit of oomph is just like, I got this. That's the requirement. That's they are achieving it. Now, only gases goes to the combustion chamber. This is a very critical aspect. Many rocket designs generally have either liquid going to combustion chamber, basically liquid oxygen and liquid fuel. Some has like, basically gaseous hydrogen and liquid oxygen. But basically, generally there would be either 2 liquids or 1 liquid, 1 gas. This puppy is kind of unique, unless there is some other designs, which I have not found that well, is that this puppy has only gas, meaning what goes into the injector is just gas. The benefit of that, gases are super easy to mix. Like turbulent gas mixture, it's like you don't have to worry about it. It's like the easiest thing to mix is gases. So having gaseous flow allows them to mix easily, burn efficiently. That's awesome. Then it has 2 of everything. There's where you get the name of full flow stage combustion. There is pre-burners, turbines, and pumps. Everything is double. Now, how do you run a rocket? You may think, okay, I'm going to take liquid oxygen. I'm going to take a liquid methane. I'm going to put that on a chamber and voila. No. All you're going to get is a freaking flamethrower at this point in time. So to get the thrust rather than flamethrower, you have to amplify that. Basically, your mass consumption has to go up. Why? When you look into rocket system, how it's going up? Well, it has 2 vectors. The stuff that is coming out, the mass of it, basically how many tons of mass is throwing out. Another is what is the velocity of that. So you have 2 vectors. You have 2 throttle valve that you are controlling. For example, in case of ion engines, it does not have mass flow, but it has super duper hyper high speed exhaust, basically 19 km per second kind of exhaust. So either you have super high exhaust or you have super high mass flow, or you can balance it in between. For example, solid booster rocket engines, those are super duper heavy. The exhaust is heavy. It's not fast but heavy. Benefit, thrust. This is like the best thing to get out of basically a gravitational well. That's GG. Then you have other throttle where you have, like, let's say a very light output. For example, hydrogen. You get a lot of velocity, but you do not get a lot of mass flow. And consequence of that, the thrust is low, but the specific impulse is high. So that's what you have to understand. That's why you want everything going from here. This is what you're throwing. That's why you need pumps. What kind of pump? To, pump that sort of mass flow to get a rocket off the ground? Yeah, sit down, relax. The one side, like the one puppy that you see in the photos, because other puppy is completely covered, it's very hard to see. The one puppy that you see is generally the fuel side, basically methane turbo pump assembly. That puppy consumes 37 megawatts. Let that sink in. 37 megawatt. One engine's one part consumes that. Oh, there is another puppy also, that is liquid oxygen pump, and that puppy consumes 31 megawatt. Now, your first thought would be, where the heck you're getting that kind of power? Well, you're not. That's the problem. You cannot have a motor that can give you that kind of power, and you can't like plug in an extension cord to orbit. So what the hell are you going to do? The easiest thing to do is basically you already have a rocket engine. This puppy has more than enough power. So what if you made a smaller version of this puppy? So this is what we call pre-burner. So pre-burner creates hot exhaust gases, which is generally cool. Now, how do you cool exhaust gases? Well, you overflow it. You either underfed oxygen, basically if you want to make it fuel rich, or you overflow it with oxygen to basically make it oxygen rich. Benefit of that is that you have whenever you burn something efficiently, which we call stoichiometric burn, basically one-on-one, like every chemical bond is properly disposed of and you have only exhaust product. It's awesome in terms of temperature. Consequence, it's hot, meaning it's so hot there is no turbine material that can survive it. Like you have to design some sort of active cooling for the turbine blades, which good luck with that, it's not happening. So fundamentally no turbine can handle it, so we overflow that puppy. How do you overflow that? That is completely up to you. So that's why it has like basically two pre-burners. Basically one puppy is for methane, one puppy is for oxygen, and they have like three things: pre-burner, turbine, and pump, specifically dedicated for that. And the ratio, when we are talking about the engine exhaust ratio, it's never done stoichiometric here also, meaning you do burn it, you do get 100% of chemical energy out of it, but you don't want temperature. That's why I specified, like what you want is mass flow, what you want is velocity. Temperature is waste for you. Like there is no benefit of having hot, like, oh my, this part is hot. You don't want it hot. Like that's wasteful for you. So what people have figured out is like it's far more efficient to overflow something. For example, if you have hydrogen, you're gonna overflow hydrogen. You have oxygen, you're gonna overflow that puppy. So this has 3.81 oxidizer overflow. Basically, if you take how much you need for stoichiometric burn, you multiply that puppy to 3.8, and that's how you get. Basically, if you are burning 1 liters of basically methane, add the oxygen you need to completely combust it, then multiply that by 3.8. So you are getting a lot of basically carbon dioxide, lot of water vapor, and insanely large amount of raw oxygen, like coming out of it. So that's just the exhaust part. That's why I specified you need basically mass flow and velocity. So you do not need temperature. Like if this part is cold, that's not an issue. As long as you are getting a lot of velocity and lot of mass flow, you good. Then we come to the backfeeding part of it. Basically, it creates gaseous oxygen. Of course, you have so much rocket exhaust going on, you have enough oomph to extract a little bit of power there. Now, why do you need this little bit of power? Well, because you have to understand, all the tanks are huge. They are building size, like multi-story building size. So at the start, they will be pressurized with helium. Now, that's the problem. That's why I said like it's a bit difficult to do on Mars. But let's say you figured it out, or you carried it with yourself, you pressurized it. But once you start to drain the fluid, and again, you are draining it like, tons per minute. So not even minute, per second. So you're gonna drain that puppy very quickly. So how the heck you're gonna pressurize it? You can't carry infinite amount of helium to just keep pressurizing it. So somebody figured out, hey, we have oxygen. What happens if you have liquid oxygen making love with gaseous oxygen? Nothing. They are inherently chemically inert. So you take hot oxygen, you pour that into the tank, and tanks get pressurized. So the inlet pressure of 4 bar is easily maintained even if you are draining it. No issue, because again, you have more than enough gas supply. Same goes with methane side. So what happens if you have liquid methane making love to gaseous methane? Nothing. They are chemically inert. So you take hot methane and you pressurize that puppy. So that's way they can reduce the amount of helium they need in pressure vessel, very little. So that's the ideal. And they can have huge tanks without having a consequences like how the heck we're gonna pressurize it. So that's just the design basics of that. Now this design is a very old design, 2018 or 19 or something, and this was made by a YouTuber, nasaspaceflight.com, and this is another design done by a basically an actual rocket engineer, and this is the closest estimate of how exactly the system works. But again, this is also older, 7/4/2019. But again, so far this is the most in detail is there, because again it also has this starting up sequence. Basically this design is how it works once it's on. How do you turn this on? You can't turn this design on. You need this. Basically, you need a lot of spool up algorithm. You need a lot of basically system that allows you to flush the system. So it has helium circuits and nitrogen circuit, purge circuit as they call it. So it has full detail, but it's too complex. This is the basically what we call the schematics of cycle estimate. So I'm gonna do my best to explain it, to simplify it to best of my ability. So we start our journey with oxygen tank. Oxygen, and be mindful, the reason why every photograph that you're seeing of the engine, you only see one unit is because the oxygen unit is directly on top of engine bell. So it will be looking so integrated, you will not notice it. You will notice the second part, but you will not notice the oxygen part. So we start with oxygen. Now again, it is pressurized. How it's pressurized, that's up to you. It's either it's in the starting phase, then it's pressurized by helium. If it's like a running phase, it's pressurized by hot oxygen itself. So you take oxygen. You take a little bit of methane, little bit, be mindful, very little, and then you burn this puppy. Now, how do you burn it? This is the very critical aspect. You overflow the oxygen to hell. Basically, you have little bit of methane, so all the liquid becomes a gas. This is a critical design architecture of basically Merlin, I'm saying Raptor system, is that the liquid flow that is happening, they're calculating is like how much mass flow that we have liquid oxygen, how much energy we need in terms of megajoule to convert that liquid into gas at a pressure of 430 bars. So they are regulating the fire to achieve that. How they are regulating it? You have a lot of oxygen and then you have methane. Here you need a small igniter, electrical igniter, to get that puppy going, and then you have the oxygen that is already gaseous. You take a little bit of bypass with some regulation to gaseous tank to pressurize the oxygen, and then this gaseous, which is around 430 bars. Now this is a very critical aspect. Chamber pressure must be lower than your exhaust pressure, exhaust of the pre-burner, because otherwise it will not go. Like you cannot, if this is 200 bar, it will backflow. So it has to be higher, 430 bars. Now be mindful, these are estimate. It's not precise. So 430 you have, and then you have gaseous going into the chamber. Chamber you will have methane and they are making love, and you have lot of pressure, 300 bars. Now this pressure is useless to you. Again, you need mass and velocity. Pressure is useless to you. So what do? We add a transformer. What is that transformer? We call it converging diverging nozzle. So you converge this puppy. So what does this do? This forces this pressure to get out of there. It's like go. But again, you are creating what we call choke flow. It's like pressure wants to get out, but it can't. It's just like limited by the geometry. It's like I have too much energy, I cannot get it out. Now it creates a sonic barrier here. Basically, it gets as fast as it can go, and then it chokes there. That's why we call choke flow. Now it's like too much pressure, too much pressure. Then you give it the diverging part. Benefit? You have 300 bars and you will have pressure drop off, like this will drop it to almost 10 psi. Basically, it will drop sub-atmosphere pressure, less than 1 bar. You have 300 and you dropped it to 1. What did happen here? Well, again, energy cannot be created or destroyed. So you just converted it. You converted pressure into velocity. So this puppy was barely sonic. This puppy could be hypersonic, basically multiple kilometer per second, 4 kilometers per second, 3 kilometers per second. That sort of exhaust flow you're gonna get out of it. Why? Converging and diverging nozzle. That's what you did. Basically, this is this part. The engine bell part is what we call transformer. You take pressure, you drop the pressure, exactly like how you take basically high amps of a generator and you amp the voltage, because again, for transmission you need high voltage. You amp the voltage up, you reduce the basically amps. You increase voltage, reduce the amps, or increase amps, reduce the voltage. Same here. You don't need pressure, you need velocity. So converge it, diverge this puppy, you drop the pressure and you get super duper high velocity. And again, you don't need basically temperature. So that's why the overflow part is there. That is so important. So this is the oxygen side. You take oxygen, you burn it efficiently enough and overflow the hell out of it, as long as you are achieving very high pressure exhaust of like 430 bars and 100% gaseous. Basically, it should only send gas to injector plate. And then you have a little bit of bypass that goes into the gaseous pressurization system and you pressurize the tank. So that's how oxygen is sorted. Okay. Then you take a little bit of oxygen pipe, and you take this little bit oxygen pipe and then you send it to methane side. So this whole area is oxygen system, and exhaust is what we call oxygen rich, meaning even if you dump a little bit of oxygen there, accidental oxygen, nothing will happen here. Why? Because methane is already consumed. So you have CO2, it's inert. Basically, this part is completely safe from oxygen itself. Oxygen cannot do anything here, and because it's completely bearing sealed to one thing, nothing bad will happen here. If you have a bearing failure, like bearing was a hell of a hassle for space shuttle engines and other engines also, especially if you have a single shaft, because again, oxygen wants to make love to other things. Here it's like, bro, methane, you already made love to it, you already have overflow, it's not going to do anything. So this part is oxygen, you take care of it. Then we come to the methane part. Methane starts the same. You already have 4 bar of inlet pressure, and then this puppy comes in. This puppy gets turbo pumped, turbocharged. And then the pressure goes into the engine bell and you cool this whole section. Basically, the combustion chamber, the engine nozzle, you cool this. Now, because you are cooling a whole goddamn rocket system, the flow which comes in as a liquid becomes almost gaseous. Whereas like, I'm almost ready to become gas. It's cryogenic input. The output is like almost ready to become gas. It's like that minus 200 to like, I'm just ready. The pressure flow is the only reason I'm not boiling. Then you send it to burner number 2. Now here you take a little bit of oxygen and you just burn it. How do you burn it? You burn it in such a way that you get 100% gasification. Exactly like how you are getting in oxygen, you get 100% gasification. That's the hope here. So you get gasification, you ignite this and you control the oxygen flow with oxygen regulator valve. You're like, okay, how I'm gonna adjust it? And then what you have is hot exhaust at very high pressure. You have 342 bars of methane, which is raw methane, and that is coming here. Now it had a little bit of carbon dioxide, but again carbon dioxide inert, not an issue. So you have oxygen going there into the chamber. Again, what do you have here? You have very high pressure oxygen, you have very high pressure methane, and both of them are in gaseous state. You have a little bit of electrical love here, boom, cycle self fulfills after you start it. How do you start it? That's up to you. That's why the second image is there. I have no idea. Basically, they have to flush the system so it does not have any contaminants with nitrogen. Then they have to spool up the turbines with basically helium, because be mindful, something will be trapped here, but you do not want it to become something that it should not, basically condensate or freeze or cause a blockage. It should not happen. So helium is best up for that. So you spool up the turbine, because without spooling the turbine, how the heck you will run this circuit? That's the biggest issue. So it has a completely independent circuit system, especially in the launch platform. You will notice there are small systems that will plug into the engines, start the engine. Only the central booster engines can restart on their own. Even on upper stage has like ignition system. The base stage, all the outer engines can only be started on ground. It cannot start on air. The only central part has the reignition circuitry. So that's the idea. You take oxygen, you burn it, you gasify it, whoosh. You take basically methane, you gasify it, whoosh, and you run the whole circuit. So it has two turbo pump assembly where you have pre-burners, turbine, and pumps. So 31 megawatt and 37 megawatt. And the oxygen is at higher pressure because again you are overflowing oxygen. So you need that bit kind of extra there. This is the basic level understanding. Then we come to the real world. So how is the real world here? Well, real world, for a brick, he flew pretty good. If you do not know that reference, I cannot help you. But reality is this puppy did amazingly well. It reached almost 40 kilometers in altitude, and engines performed admirably. There was some issue specifically with the ground platform, that there was a lot of damage at launch. So many engines malfunctioned out, flat out. They were like boom. But all other engines performed admirably. They literally boosted themselves up to a point where they were able to save the mission, which it had so many engine failure. I think 5 or 6 engine failure was there at its last moment, but it was still going, like it was doing what it needed to do. So it had very good, admirable performance, and failure was compensated. And this is the same engine that was like, becoming what we call engine rich exhaust in Mach 1 variants. So this was Mark 2 variant, and they are working on Mark 3 variant as we speak right now. So surprisingly good performance in real world reality. So what we can expect in future? Well, here's the max powered is fuel, because you know how much megajoule energy you have when you're talking about, like, let's say 1 liter of methane and 10 liters of basically oxygen. You know that. Like, the only vector you can truly change is basically combustion rate. You can burn it super fast to get more out of it, but problem is these things are designed for sensitive. It's not designed for ICPM. ICPM has the maximum throttle, where you go bonkers as hard as you can. These things are not designed for that. So fundamentally, you know how much oomph you're gonna get out of it. So do not expect like future versions of basically Starship to magically go from same way we went from like early versions of Falcon 9 to from 10 tons to 20 tons. It's very low chance that it will happen here. It could still grow, but expect it to be generally under 150 tons. Like, that's hyper optimistic. Because again, Merlin 1, they were learning a lot. This one is like Mark 2 project of a Mark 2 itself. So fundamentally, they have learned a lot. So the amount of optimization they can do is not that much. So what they are working on right now, what is the biggest difference from Mark 1, Mark 2, Mark 3? Well, it's the flow rate. Everything is about the flow rate. While in principle, you will like, okay, I'm going to have a pre-burner here. Pre-burner is going to drive the turbine. Turbine is going to pressurize it. And we're going to have this amazing love here. And outcome is like, sir, you are only getting basically 180 bars rather than 300. It's like, what the hell happened? Pressure drop, flow restriction. So those things that they are optimizing. That's why they are removing as many pipes as possible, as many bend as possible, as many flanges as possible. Everything is about flow. If you can just make it flow, it's going to be awesome. Same amount of energy, same amount of chemical energy is released, but you're going to get more work done if you have better flow. That's the whole point. Everything is going to how the heck we make the gas flow, liquid flow, propellant flow, all those flows as efficient as possible, as low pressure drop as possible. And efficient system efficiency like of auxiliary system, for example gimbals, how much energy this puppy consumes, that also has to go down, because here's the outer ring of engines do not have gimbal. The only core engines have gimbals. Outer engines are surprisingly dumb, like they cannot even start. They are like, that's why they have quick disconnect that connects to engine itself, spools up the engine, starts the engine. Once it disconnects, the engine is like on. Either if you turn it off, like let's say computer control commands it to turn off, they cannot restart it. The restarting circuit is in the basically launch pad itself. Efficiency of auxiliary system matters here, specifically gimbal, because again gimbal consumes a lot of energy, either in terms of hydraulic pressure or maybe future designs of electronic actuations. It does consume energy, and the less energy you consume, the more oomph you get to send for payload to orbit. So it's generally much more wise to optimize it, improve the efficiency. This whole system is about efficiency, because here's the deal. The outer rings do not have gimbals. Be mindful of that, and they cannot even start on their own. They need ground connection to start them. Only the center wall have the gimbals and ignition system. Now, what does that 300 bar means? Does that mean that they're gonna actually drive it at that hard? Hell no. What they're gonna do is drive it as low as possible. Basically, as bare minimum stress as possible, because these rocket engines have to be what we call reused. It's not space. Basically, SLS engines are driven much harder than compared to same engine compared to space shuttle. Why? Space shuttle was designed in such a way that it's gonna come back, those engines will be reused. So they wanted that engines to be like in good condition. You do not want to like go balls to the walls. Here is the same thing. They will design it to handle balls to the wall, but they will never be like go all in. The idea is there, it's all going to give them an emergency thrust margin. What does that mean? Similarly, they launched it and multiple engine failure happened for some reason. At that point in time, computer will have an option before it does terminate flight. Before it goes flight termination system, it's like, instead of flight termination, let me try to boost all engines to full power. Basically, it's like nitro booster of them. Rather than like limiting to 300 bars, all engines go all out to 350 bars. But let's say, wouldn't that shorten the lifespan? Here's the deal. If rocket is about to go off, it's going to go into boom territory. So everything is better than boom. So if they can achieve extra thrust, even by few percent, that could allow them to gain enough delta V that mission can be salvaged. That would be much better off, because ideal is you launch the rocket, you do the mission, everything is recovered. That's ideal. The least ideal option is you launch the mission, but some failure happened and engine had to compensate. They're self-destructed, they ran out of fuel and propellant, and they're like, okay, they're crashing, but at least your mission was saved. That you will still get paid for it. It's still good, but it's okay kind of scenario. Worst is like you launch it, computer detects that it does not have enough thrust because the engine's high, and then it's like, okay, I'm self-terminating. So these three options, like sacrificing that longevity of the engine and even the mission, like even the recovery part of the mission is acceptable, because again launching the thing is more important. So that emergency thrust gain also, either it is used as longevity or used as emergency booster. So in both scenarios, it's a good engineering decision to have that oomph, that extra oomph. Be mindful, this is the same concept in almost all fighter aircrafts. Like they have a normal settings where you can run them 24/7/365, and then they have like go balls to the wall. Like if you're gonna be boomed by a missile, you really do not need to worry about jet engines lifespan. So there is a override function where it's like computer just gives you control, go YOLO on it. So that's the same thing here. Like engine will have the range, and that range will be locked most of the time. But if it's like, whoa, we're about to go boom, go full YOLO, they can do that. And the core focus of the Starbase is no longer making most powerful engine as possible. They are not focusing on that. We are no longer in that prestige era. The core focus is manufacturing improvement. Can we make this puppy? Can we make this puppy as fast as possible? Can we make this puppy last as long as possible? As efficient in terms of material consumption as possible? Because again, it does require some awesomely complex alloy to survive that. So you do not want to just consume a lot of it. So longevity, ease of reuse purpose. The ideal is this puppy lands and they refuel it instantaneously. Now, of course, that is stretching it a bit. Generally, you will need 1 hour of downtime. And that's their hope, that instead of downtime of like few days, they have downtimes of hours. That's the hope. That's what they're working on. Do not expect them to like, this rocket was like 150 ton when we built it. It became 250 ton like at the end of his life. Now, that's very, very idiotically unlikely to ever happen. So all their aims is make this as efficient as possible, make this as easy to make as possible, make it as long lasting as possible. So this was my presentation on basically Raptor 3. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.